In this section we look at absolute value functions, and we're going to look at absolute value functions of both linear functions and quadratic functions. So we'll start off with just looking at a linear function, y equals x plus 2, and we'll compare that to the absolute value function y equals the absolute value of x plus 2. So if you make a little table of values and think about a few different x and y values, if x is equal to negative 4 all the way up to 1, let's say, negative 4 plus 2 is negative 2, and then we have negative 1, 0, 1, 2, 3. This is pretty straightforward, and we can graph this very easily. If we think about the absolute value function and plug in the same x values, negative 4, negative 3, negative 2, negative 1, 0, 1. If you recall, the absolute value just simply strips the negative off. It makes a negative positive, and it doesn't do anything to an input of 0 or an input that's positive. So if you look at the table on the left, when the y value is negative 2 and you take the absolute value of it, you get positive 2. And then when it's negative 1, you get positive 1. But then the rest of the table, from 0, a y value of 0, on down, the absolute value bars really don't do anything. And so this part of the graph here is going to look identical to the graph of just y equals x plus 2. However, there's going to be a difference in the numbers that are at the top of the table here. So let me just move this over to give us a bit of room. If we look at the graph, and we start off with the graph of y equals x plus 2, that's a straight line crossing through the y-axis, or the y-intercept of 2, and it crosses through the x-axis at an x-intercept of negative 2, and that's going to be a very important point. It's going to be called a critical value, and the reason for it is that if you look at the graph of the absolute value function, there's no y values that are negative, and so it's almost like we can take this line and just erase it all the way up to the x-axis and then replace it with a reflection. So on the right, this part is identical to y equals x plus 2, but on the left, this is the negative of x plus 2. Now if you put a negative sign in front of the whole expression x plus 2, you get y equals negative x minus 2. So if you think about that line in terms of slope-intercept, the slope is negative 1. Sure, that line looks like it has a slope of negative 1, and we can verify over on the right, looking at the first two entries of the table, that it does have a slope of negative 1. And if you were to continue it down below the x-axis, it would cross the y-axis, certainly at a negative value, and negative 2 is a perfectly reasonable value since it hits the x-axis at negative 2 and it has a slope of negative 1. So it's almost like we've taken the linear function and we've broken it into two pieces. And this language of breaking a function into pieces is going to be important for absolute value. And we're actually going to see a different notation. So in fact, we can write this function using what's known as piecewise notation in the following way. So we use what looks like the opening of a big pair of braces, but we're actually not going to use the right hand brace. We're just going to use the left hand brace, and we can write the two different linear pieces that we can see above. We have minus x minus 2, and we have x plus 2. But of course, we don't have all of those linear functions. The minus x minus 2 essentially stops right at that critical point, negative 2. And we indicate that by just putting a little comma in and saying that the function is negative x minus 2 as long as x is less than negative 2. And then after we cross the critical point, the function is just y equals x plus 2. And so as long as we are to the right of negative 2, then we just have the function y equals x plus 2. So we can think of the absolute value function, y equals the absolute value of x plus 2, as two different linear functions, but we're only taking part of each linear function. Now, the one thing I haven't indicated on this piecewise notation is, what about the critical value itself, negative 2? Well, turns out that it doesn't really matter. We can be a little sloppy here because whether or not we include that with the leftmost piece or the rightmost piece or both doesn't really matter. I mean, it essentially is a point that belongs to both lines. However, typically you will see the greater than or equal to sign used. In other words, it's almost like you tack that point onto the function on the right. But truthfully, it doesn't matter a whole lot because it is a point that belongs to both functions. And so if you included it with one instead of the other, wouldn't make a difference. If you want to include it with both, that's probably fine too. All right, let's see what happens with a quadratic as the argument to the absolute value function. So let's say we have y equals absolute value of x squared minus x minus 6. Now, in order to understand what's going on here, let's do a little graph. Now, if we're going to do a graph of that quadratic without the absolute value bars, y equals x squared minus x minus 6, I'd like to know where it crosses the x-axis. And where it crosses the x-axis, we're going to refer to as critical values. So let's do the critical value calculation. The critical value calculation is one that you've done many times before because you're just setting the y value equal to 0. In other words, you're just finding the zeros of this function, x squared minus x minus 6. And you can do it any way you like. You could use a quadratic formula, but in this case, this trinomial factors quite nicely as x plus 2, x minus 3. And so if x plus 2 is 0, that means that x is equal to negative 2. And if x minus 3 is 0, that means that x is equal to 3. Once we know the critical values, it makes it very easy for us to do a nice sketch. We know that it passes through the x-axis at minus 2, and again at positive 3. So what's the purpose of finding these critical values? You can think of the critical values in this case as being the dividing points between where the function is positive and where the function is negative. And where the function is positive, you don't have to do anything. The absolute value bar is not going to change the function. But where the function is negative, the absolute value bars essentially reflect the function through the x-axis. They strip away the negative sign, which makes all the negative y values positive. And so any part of the graph below the x-axis ends up getting reflected above the x-axis, and we lose everything below the x-axis. So if we know the critical values, then we can write this function in piecewise notation. We've essentially got three branches here. And the branch on the left, which is all the x values less than negative 2, there's no change. It's just x squared minus x minus 6. The branch in the middle corresponds to everything between negative 2 and positive 3. And what's happened? Well, we've reflected it, meaning we've put a negative sign in front of it to change all the negative y values to positive y values. And so we can just change the signs on all the coefficients here and write this as negative x squared plus x plus 6. And then the branch on the far right, which is all the x values greater than 3, well, again, we just have the quadratic that we started with, x squared minus x minus 6. Again, I haven't included the critical values because it doesn't really matter where I include them. You may see some presentations of this material which, again, always sort of try to attach it to the right-hand part, in which case you'd put a less than or equal to there, and you'd put a greater than or equal to there. But these are fussy little points that, quite frankly, don't matter, because the point negative 2, 0 belongs to both x squared minus x minus 6 and negative x squared plus x plus 6. So in truth, it doesn't matter where you put it. And you could attach it to all of the intervals. You could change all of these signs to less than or equal to, greater than or equal to, and that's fine if you want to do that. Now, there's one little thing we can do to make this a little bit more compact. We can combine the first and third lines there, because essentially we've basically got two scenarios. In one case, we're not doing anything to the function, and in the other case, we are flipping it. So you've really just got these two functions, x squared minus x minus 6 and minus x squared plus x plus 6. So the minus x squared plus x plus 6, you can see, is only when the x values are between negative 2 and 3. And the function that we essentially started with, x squared minus x minus 6, that's still present as long as x is less than negative 2 or greater than equal to 3. So essentially all we're doing is combining the first and third lines of the piecewise notation above. Now, it's really important that you play around with this with some graphing software or your TI-83. If you use Desmos and you want to graph an absolute value function, you can click on the Functions button over here, and under the Miscellaneous tab you can see ABS. So instead of using the absolute value bars, it treats it like a named function, almost like sine or cosine, and the argument to the function is in brackets. Now this is true also on your TI-83. I'll pull that up in a second. So I've got the two functions that we looked at, and let's see just on Desmos what these look like. There's your line, y equals x plus 2, and here's the absolute value of x plus 2. You can see how it doesn't change anything except it takes the part that was below the x-axis and it reflects it up. So in other words, to the right of the critical value, nothing changes. But to the left of the critical value, everything that was below the x-axis gets reflected and is now above the x-axis. Let's see what happens with the quadratic. So with the quadratic, we've got the parabola facing up, crossing right there through the x-axis at negative 2, and then again coming back up over there at 3. The absolute value of this function doesn't affect the left or right branch that's already above the x-axis, but it flips the part below. And you can see that that part below gets flipped up. So on your TI-83, you can do the same thing. To access the absolute value function, you can access it through the math menu, but probably the easiest way to do it is just to access it through the catalog, especially because the functions, all the functions that are available to you in the TI-83 are sorted alphabetically, and the absolute value function is the first one on the list. So to access the catalog, hit second 0, which brings up the catalog, and there's the ABS. And now you can plot the absolute value of anything you like. Let's do the same function we did on Desmos, x squared minus x minus 6. And we better change the window settings. So we can zoom this to standard. And there you can see it comes down, it kind of bounces and goes back up again, almost like a little, the starting of a Batman symbol perhaps. And so I think you'll find it a little easier to play around with different options on Desmos, but you can certainly graph these on your graphing calculator as well.